Okay, today is delayed session. Supposed to be on Monday, with 7, and so this session kind of deals with something kind of important in deep learning. Specifically deals with bias variance trade-off, which is also known as model complexity versus overfitting, right? It's a very uh, well-known problem, gradient descent based, heuristic based learning systems, right? So it's uh, it, it's encapsulated in these two terms called bias and variance. Bias measures how well the model can capture, can match the target of flow. Of course, when we are talking about target here, this target refers to the training data set, right? So it basically captures how well the model is able to perform on the training data set. And variance of the model captures how much the model depends on the training data, right? So variance is basically if there is a small change in the values, then the model output will vary significantly. If the variance is high and input value changes slightly, then the model output will vary wide, right? Which is typically not a good thing, right? Because it means that when you run the model on the test data out of distribution uh, data, you can get widely different outputs and they are more likely to be incorrect, right? So variance will basically give you an indication of how well it's, uh, it's going to generalize outside the training data, right? So there is a trade-off which is called the bias variance trade-off, and conceive given a model f of x that tries to predict the value of some y, the mean square error of this model is given by bias square plus variance plus some sigma square, which is some uh, parameter, right? It's like something that you add. It's like a noise parameter, right? So given this expression, the question is, what is the characteristic of a good model, right? Obviously, ideally, you want a model to have minimum error, right? You want this y minus fx, the expectation of y minus fx whole square to be as low as possible, right? But turns out that there is a trade-off in between the bias and variance, right? So while you want, well, ideally, what you want is this option C, which is low bias and low variance, in which case basically you'll have the minimum value of the error. What you can actually realistically get is optimal values, right? So you can only get like optimal values of bias and variance because uh, as you increase the complexity of the model to map the training data more and more and thereby reducing the bias, what happens is that the model becomes increasingly dependent on the values in the training data, which means your variance goes up, right? So you are reducing the bias, but your variance is blowing up, and at some point, uh, you are no longer able to reduce this total sum, right? Where the variance overtakes the increase in the variance overtakes the reduction in the bias, and your error starts going up, right? On the other hand, if you make your model simpler and simpler, of course your variance will go down, but your bias will go up, right? Because the amount of expressivity of your model reduces as you make it simpler, right? And this trade-off is very effectively showcased in this particular plot, right? It's not a real this plot is not like a real example, but it is something that you often see. In fact, we can I am planning to run some code once we are done with like the questions. We'll train a model on a simple classification data set, and we will see something very similar, right? So we will see that this trend that you're observing over here, it does in fact occur. Uh, uh, so here, so this basically you see, this is model complexity, right? So as you increase in the x-axis, what is happening is that your model is becoming more and more complex, more and more powerful. And on the y-axis is the error, which is this entire whole sum, right? Obviously, if your model complexity is very low, then your bias term will become very high, right? Because it cannot map the training data effectively. And you have high error. And on the other hand, if your model complexity increases too much, what will happen is that your variance will become high, right? Even though your bias reduces over time, your variance will become high and will kind of cancel out and in fact make the error big, right? So this is what happens. Basically, your training error will continuously go down as you increase the model complexity, because you're making it more and more capable of capturing all the information in the training dataset, right? But test error will only go down until a certain point, right? Which is the optimal value for bias and variance. And then what will happen is that it will shoot up, right? So on one side, you have high bias, low variance point, which is where your model is too simple. And on the other side, you have high variance and low bias situation, which happens when your model is too complex, right? So in both of these cases, your error will be high, right? Your error on the test data set, on the out of distribution samples that you actually want to predict something, right? So there is another, the bias variance is one way to describe this. Another way to describe this is uh, on this side, where the models are simpler than required. Uh, this is called underfitting, right? So you have underfitted to the data. That's why your error is too high. And on the other side, where you have high variance and low bias and very high model complexity, this is called as overfitting. So here basically have overfitted to the data, overfitted to the training data, and that's why its performance in out of distribution samples is very bad, right? So this is underfitting, this is overfitting. Overfitting corresponds with high variance and low bias. Underfitting corresponds with high bias and low variance, right? So this is how these terms kind of interplay with each other. And it's important, right? Because when we ask you, I have a model, this is the characteristic, what has happened to the bias and variance, is it overfitting or underfitting? And then you should be able to match the concepts and answer, right? So yeah, so this is a brief introduction on the terms that we have. So based on this, we'll see a few questions, right? So first of all, another question that is kind of very related to the plot that we were discussing. Which of the following statements are true about the general trend of training and validation errors, right? So it decreases by validation error decreases to zero by increasing the complexity. Training error can be reduced to zero by increasing the model complexity. Validation decreases up to a certain complexity, after which it starts increasing. Training error decreases to a certain complexity. So we saw this before, right? So we saw that this is based on the same plot, right? And we found out, we have seen before that the first thing does not happen, right? Uh, no matter how much complex you make the model, validation error is not going to go down to zero. Instead, it will have like an optimal value and then it will keep on rising. So it's not A, but of course, training error can be reduced to zero because the training data set is finite, right? So if you keep on increasing the size of your model, what will happen is that each of the each sample data within the training data set will be uh, representable uh, inside your model separately, right? So there will be like a separate, they can be in the worst case, there can be a separate path that activates for each sample in the training data set that the, the, that basically connects it to the correct outcome, right? That's what happens. That's what can happen if your model is extremely complex, right? And in that case, what happens is that it's just a mapping, right? And then because it is just a mapping and because it is so highly dependent on the training data set, it will perform very, very poorly on out of distribution samples, right? Because the out of distribution samples will not have a proper mapping, right? Because you have not generalized uh, the learning sufficiently. So training error can be reduced to zero, right? And this is something you might come across a lot when you are training your models, let's say, and you will see that my training loss has gone down almost to zero, and my training classification performance is almost 100%, right? In some cases it might even be exactly 100%, and you might feel that, oh, I have done an excellent job. But the problem is that you might have overfit. So it's always important to divide your data set into training and validation, right? So you divide it into training and validation data, and then you train on the training data. You do not train on the validation data. You use the validation data to try to figure out how well your model performs on out of distribution samples, right? So that validation data set basically creates a what is called as a sanity check, right? It makes you, it makes you evaluate your model in a more honest, uh, more effective manner, such that that is more useful uh, to what you actually want to use the model for, right? Because obviously you're going to deploy the model on out of distribution samples, and for that, the performance on that can only be estimated based on the validation error, right? So yeah. uh, Given, so this is an example of the same kind of graph. You have uh, on the y-axis you have training error or training loss, and there are 3 points that have been identified on this graph, ABC. The question is which of these points represents like a good model, right? Note that on the x-axis we have model complexity, right? So each of these points represents a model with certain amount of complexity, and the question is which of these is like a good model that you can use, right? So this is so now we are kind of, so now the question is kind of building upon the concepts that were discussed in the earlier uh, points, earlier questions, right? So why don't you guys kind of think about it and answer based on the previous discussion? uh, I'll give like a minute or so for you guys to work it out, and then you can post the answer in the messages, right? And then I will, of course, discuss those solutions. Yeah, so based on the previous discussion, obviously, I mean, based on the previous discussion, it should be fairly obvious that what you do want is this situation B over here, right? Because, you know, remember that A would typically refer to a underfitted solution, right? And anyways, you can see that even the training error is high, right? Which means that the validation error is also most likely going to be pretty high, right? So A is underfitting. C is very likely to be overfitting because you have increased the model complexity greatly and your training error has almost gone to zero, right? So this is very likely to be an overfitted solution where, you know, validation error will again jump up. So the most likely option, like the safest bet out of these three choices is B, right? Which is more likely to be in uh, optimal situation, right? So yeah, so at A you'll have high bias, which is underfitting. At B you'll have high variance, which is overfitting. At B you might get a better solution. I mean, you most likely get a better solution at B compared to A or C, right? So yeah, so now that we have identified the problem, right? We now have to think about how do we solve this, right? Because obviously you cannot put your hands up and say, oh, variance is going to be high, I can't do anything about it. We have to solve it, right? And of course, bias, we already saw how we can solve for bias, right? How we can reduce the bias, which is to say that you simply make your network larger and larger, right? So you make the model more and more expressive. If you just increase the model complexity, it, it will reduce the bias, right? Uh, but of course, you know, this increases the level of variance and overfitting in the model. So the question is, how do we address overfitting, right? And here we have four options. One is you collect more data, you do regularization, data augmentation, which is similar to collecting more data actually, right? The difference is that when you collect more data, you get authentic new samples. When you do data augmentation, you get synthetic new samples, right? So it's like you are generating new samples data, out of the data that have already been given, right? And B is regularization, which I think we have talked about in a previous session about specifically about autoencoders, right? Because we talked about over-complete autoencoders and how you would require regularization to make them work, right? So that's regularization, right? And D is use item optimization, right? So yeah, and obviously, you know, if you remember things something about regularization, then of course you obviously point with that as the solution, right? One thing that you can directly uh, remove from this is to use item optimizer because that's just going to change uh, how the training happens, right? It's just going to either make the conversions faster or slower, right? Most likely, item optimizer is pretty good, so it will most likely make the conversions faster, but it does not do anything in regards to reducing variance or in dealing with overfitting. So that's not going to help, right? Obviously, regularization is going to help because when you do regularization, you have you're basically you're constraining the weights, right? So you're constraining the values that the weights can take, right? Which means that you're constraining your model in a sense. right? Which makes your larger model somehow slightly more equivalent to a smaller model, right? So that's how regularization kind of makes reduces overfitting. So regularization obviously on is one of the answers, but it turns out that collecting more data also has basically the same effect, right? So the answer here is actually either you can collect more data, or you can do data augmentation, or you can do regularization. In all of these cases, your model performance will actually improve, right? Regularization is fairly straightforward, why that will help, right? The other things is for the other things you have to think about. So for regularization, you're only thinking about the size of the model, or the expressivity of the model, which that regularization constrains the values that the weights can take, which means that it kind of constrains the model. So that's how it deals helps you to deal with overfitting, right? For data, you have to think about the relative size of the training data versus the model, right? So your model is of a particular size, right? And your training data is of a particular size, right? So if your training data is training data set is extremely small compared to the model size, right? And I'm talking about relative generic terms. I'm not talking in like a dimensionally, with dimensions or things like that. But I'm just speaking in a general sense, right? So if the training data set is small with respect to the size of the model, what will happen is overfitting, right? Because the number of training samples that are there that can that are to be mapped by the model is very small. So the model will overfit on the data. Whereas if you increase the training data set, right? So you just capture more and more samples. Now your training data set is extremely large compared to the sample. It will no longer overfit, right? Because now there is no way that this model, which is relatively small compared to the training data set, there is no way that this model is able to uniquely represent every data sample that is present in the training data set, right? So collecting more data does help in reducing overfitting. It does help in improving the performance on uh, unseen out of sample uh, out of distribution samples, right? And in fact, it is pretty much the holy grail of improving performance, right? So it always, I mean, so far at least, it has always come down to how much data can be used to train the model, right? That's why when you hear about these latest models, right? The foundational models, large language models, and everything like that. Chat GPT-4 or whatever, all the GPT variants, right? They have been trained on tremendous amounts of data, right? They have been essentially trained on like everything that is present in the internet, right? And that's why they are uh, so capable, so powerful, because it's an extremely large model, right? So it's a huge model, and the data that the model is trained on is even larger, right? So it's like the model itself is has some hundreds of billions of parameters, and the data that it is trained on is like trillions of tokens, right? Which is like all the text that is present on the internet. So yeah, so whenever a problem arises of improving performance, the first and most like capable thing that you can do, most effective thing that you can do is increase the amount of data that you train your model on, right? And you can do it in a synthetic way, which is where data augmentation comes in, right? But it will have less of an advantage of efficacy, but it will still help, right? So when this is very, very common standard practice, that when you train something, when you train a model, you always include some sort of data augmentation in it, right? So for example, if you're training image classification model. The data augmentation could be that you will slightly rotate the images, you will shift the images, you can crop the images, you can stretch the images, right? You can do all sorts of combination of all sorts of operations. You can flip the images and take the mirror image uh, in a horizontal or vertical way, right? So you can apply all of these things, and basically what happens is that every uh, every augmented or every uh, sample on which you have applied certain uh, operation, that is like a separate sample, right? That's a completely different image that the network has to learn from, right? So that's how data augmentation actually improves the performance, right? So yeah, so this is what you have to keep in mind. So don't get blindsided just thinking about regularization, because of course regularization does work, but what works more is increasing the amount of data that you use to train the model. So here is a similar question, right? So we are training a neural network model and you get 100% training accuracy, which is not uncommon. It is actually fairly common to get extremely high training accuracies, right? But your validation accuracy is very low. It's like 35%. So the question is, how do you reduce the difference? And of course, if you want to reduce the difference, first thing you have to do is diagnose the problem, right? You have to understand why this discrepancy has arisen, and then you can apply suitable techniques to solve the problem, right? So yeah, there are some options: optimizer, activation functions, uh, and dropout. The question is, which of these is going to be the thing to choose for this problem. So yeah, so here, of course, you know, like I said, first we have to diagnose the problem, and then we can think of what would be the solutions, right? So you get training accuracy of 100% and validation accuracy is very bad at 35%. This means that your model has overfitted, right? This means that you have gone into that complexity, high complexity situation where your bias is extremely low, but your variance is high, right? Because that is what is meant by 100% training accuracy, right? It means that your loss training error or training loss has become extremely small, right? Which and basically every sample in the training data set is being identified correctly, But at the same time, your validation accuracy is very low, which means that you have overfitted to the training data and it's performing very poorly on out of distribution samples, right? Which means that the way you solve it, obviously, is by using regularization or using the training data like we discussed earlier. Uh, Out of those two options, uh, the only option that is available among these options is dropout, right? Because dropout is a regularization technique. Basically, what dropout does is that it forces certain fractions of neurons in your network to become inactive, and the neurons that should become inactive are like randomly chosen for every uh, batch, right? So for every batch that you do, for every training batch, you randomly switch off a certain fraction of neurons in your neural network, and then you try to work with that, right? So this disturbs the model. This makes the model, so during training, it makes the model kind of smaller, because let's say you're cutting down half of the neurons, right? So it is kind of reducing the model size by half effectively during training. And then at inference time, you don't do dropout, obviously, because you want all of the neurons to be uh, possible of generating activations. And what happens is that then it becomes a more powerful model at inference time that is not overfitted quite as much as when you what you would originally get, right? So dropout is the answer here. The other things really don't matter, right? Because all of these things, right? RMS prop, tannage, sigmoid, whatever. So all of these things would affect the training performance. And what we have already is a situation where the training performance is extremely good, right? So we don't really need to change any of these things, right? Because what will RMS prop optimizer do? It will either speed up the convergence of the model or it will slow down the convergence of the model, right? But we already know that the model converges very well on the training data. So same for changing the activation functions. We already know that we have a setup that can minimize the training loss to almost zero, right? So none of these will actually be effective. What will be effective is introducing dropout, which is a form of regularization, and you'll have like a better solution, right? So the another way of dealing with overfitting is something that is called parameter sharing, and we will see an example of this. Like I will try to show an example of this happening. So parameter sharing is basically the what happens when you have a lot of input neurons, you and instead of having like the separate parameters for every input, every input to output combination, you have this certain small number of parameters, and you share that, you use that repeatedly over the input, right? So that's parameter sharing. And the question is, which of these following architectures, right, uses parameter sharing like in a default manner? Uh, and you can call it, you can say that parameter sharing is a form of regularization, but it really is not. What happens is that what happens in parameter sharing is that you can have a very deep network, right? You can have a deep network with a lot of neurons, right? But you will have very few parameters, right? So the model complexity enters kind of a weird space, because on the one hand you have a lot of neurons that can uh, that can encode features, that can encode the data features of the data. But on the other hand, you have very few parameters uh, that can also do the same thing, right? So yeah, so the question is, which of these following kind of architectures uses parameter sharing uh, with- by default? And is it like feed forward? So till now we have mostly seen feed forward networks, which is where every neuron in the previous layer is connected to every neuron in the next layer, right? So you have n by m uh, size weight matrix where n is the size of the previous layer, m is the size of the next layer, right? Autoencoders can be any kind of neural network, right? Autoencoders need not necessarily follow a given architecture. Recurrent networks typically are feed-forward type, or rather fully connected networks. They have every neuron will be connected to every neuron in the next layer. Uh, Additionally, it will also have feedback loop connections with its own within its own layer, right? So it turns out that the network architecture that naturally does parameter sharing by default, in fact, is convolutional architecture, right? Where so in convolutional architecture there is this concept of filters, right? So the concept of filters is actually kind of derived from the field of image processing or conventional image processing from the days of before deep learning, right? And the idea is that you have a certain kind of filter, you apply it throughout the image with a given step or stride, right? So that's how you kind of generate the next layer activations, right? So you have a certain filter. Filters are usually small, so they are like, so if an image, the input image to a convolutional network can be can be pretty large, right? So it can be so in MNIST, for example, it will be 28 by 28 image that is input to the network. For others, for ImageNet, it is much larger. It even larger. It's like 224 by 224, right? But the filters typically will be small, right? So you are using 3 by 3 filters, max maybe you use 5 by 5 filters. And what happens is that the same filter is applied throughout the image, right? So if you consider two uh, two like neurons in the next layer in the convolution output, then the filter that is used to generate this pixel is the exact same filter that is used to generate this pixel. And in fact, it is the exact same filter that is used to generate every pixel in this convolution output, right? So what this means is that this small number of parameters, this small number of filter parameters are actually shared throughout the input image, right? Which is what is defined as parameter sharing. And uh, additionally, what this means is that even though the number of neurons, right? So the number of neurons here is pretty large. The number of neurons here is also pretty large. Even though the number of neurons is pretty large, the number of parameters is actually very small, right? So you just have this small filter sized number of parameters. uh, then this one is about early stopping, which is a technique where you stop your network training at a certain point when you so it's a heuristic technique uh, where you try to identify the point where your network has minimized the validation loss as much as possible, and then you stop the training, right? So you you can set this thing called as the patience parameter, which basically says how many steps you're going to wait for the validation loss to improve further before you stop the training. And yeah, so here, so basic idea is that you hit a certain uh, minimum amount of validation loss, and then you wait for the patient's parameter number of epochs, right? And if the performance does not improve within this patient parameter number of epochs, then you stop the training, and you don't keep this model. Rather, you keep the first point where you had achieved that minimum validation was, right? So here, what will happen is that you will enter this patient's parameter stage at this point when you have hit this 1.9 validation loss, and then you will wait for 3 epochs, and after epoch 5 you will run out of patients essentially, right? So at epoch 5 you will run out of your waiting capability, and you will decide that, okay, at this point, at epoch 2, I had the minimum validation loss. I'm going to return the model as it was at this point of time, right? So that's what this is early stopping. This is a heuristic method. uh, it basically, if you remember that plot, right? So you have training loss going down, you had validation loss going down up until a point, and then going up again. Um, that was the plot was original plot was against model complexity, but the same kind of plot can be also be noticed if you plot epochs on the x-axis and loss on the y-axis, right? The training loss goes down as a function of epochs. The validation loss goes down as a function of the epochs, and then it kind of rises a bit, and it may go very high. I mean, it may continue to rise, but most likely it kind of stabilizes or enters like a saturated high validation loss state, right? So yeah, so this is, so based on that, so we'll train one model and we'll see uh, what kind of happens over here. Finally, dealing with overfitting. So talking about dropout. Uh, so this is basically how dropout works. So you have a layer of neurons in the neural network. You in this example, you have 6 neurons, right? And you turn off certain of these neurons, right? So you turn off, in this case, 3 of these neurons. So blue neurons are active and gray neurons are inactive, right? So the output of these gray neurons, irrespective of the input going to them, the output of these gray neurons will always be 0, right? So they do not contribute anything to the neural processing that is going to happen in your network, right? So this is how you can implement dropout. And what this is called is like a thinned network or a thinned layer, right? Because you now only have 3 neurons to represent the information rather than the 6 that you originally had. So here is a very simple problem. Given that there are 25 nodes in a network, how many thinned networks can be formed? Right? Uh, how many kind of thinned networks? Because remember that every configuration of these off neuron states and on neuron states, right? Every configuration basically generates a different network, because only certain neurons are active, and then if the configuration of active neurons is different, then it will be a different number of different ordering of active neurons that are active, and that will kind of generate completely different flow of information. So it will be like a different network, right? So given that there are 25 nodes, how many thinned networks can you form by randomly switching off certain nodes from your in your network? So in this case, basically what you're doing is, so you have 25 nodes, and each of those nodes can either be on or off, right? So there are two possible states for each of those nodes. So the total number of possible configurations that you can have obviously is 2 raised to the power 25, right? Which is also, like how many, like if you treat the nodes as like a uh, binary number, then it is like how many configurations of 1 and 0, how many configurations you can build with 1 and 0, how many numbers you can represent by 25 bits, right? Which is nothing but 2 to the power 25. So the correct answer is 2, right? So that is the number of thin neurons that we can represent with this, right? So that is the end of thing. For benefit of latecomers, I will briefly go through the material once again. So this week we are talking about bias and variance, right? Bias is defined as the error, as how well the model can represent the target, and the target here talks about the training data, right? Targets within the training data. Variance is basically a measure of how much your model output is dependent on the model input, right? Which means that if your input changes slightly, how much does your output change, right? So if your output changes rapidly, widely, when your input changes slightly, that means that your model has a high variance, right? Uh, and both of these terms together actually define what is called as the error, mean square error of a model that is trying to predict some value, right? So it turns out to be bias square plus variance plus some noise term. And while you want to reduce the mean square error as much as possible, it is not possible to have low bias, and it's not possible to simultaneously reduce bias and variance uh, indefinitely, because these two terms have a trade-off with each other, right? So if you reduce bias too much, what happens is that you end up increasing the variance, right? You increase, if you, for example, increase uh, the network complexity, if you increase the model complexity too much, so your bias will go down, right? Because your the model can represent the data that is being uh, given for training. But what will happen is that it will become increasingly dependent on the input data, and the variance will go up, right? So your model performance overall will suffer. What you can do uh, instead, what you would have to do instead, in fact, is you have to settle for optimal values for bias and variance, which is kind of represented by this thing, right? So basically, as you increase the model complexity, your training error can go down to 0, but your test error will only go down until a certain point, and then it will increase, right? Because your variance will go up even though your bias has gone down, right? So this is the trade-off. It's commonly called as the bias variance trade-off. And this question, so the next question is based on the interpretation of that same figure that we saw earlier, which talks about what you can expect, right? So yeah, so you can reduce the training error to 0 by increasing model complexity, but validation error only goes down to the certain, right? And then it increases. Then similar question, but here you're tasked to uh, choose which of these points, right? So you have A, B, and C, which represent different models, obviously, because on the x-axis you have model complexity, right? So A is a uh, very simple model. It's a low complexity. B is some medium complexity. C is a high complexity. And you see that training error is going down as you increase the complexity, which is expected. So the question is, which of the following models should be chosen? And based on the previous discussion, obviously you default, right? Because you know that is uh, too A is too simple of a model. It is underfitting, right? It has high training error, which means it has high bias. Uh, so it will have high error. C is, it has extremely low training error. It is likely to have a high amount of variance. So your performance will be bad, whereas B is more likely to have the optimum mix of both of these, right? The next part is, uh, you know, obviously you can reduce bias by increasing model size, right? The question is, how do you reduce variance, right? Which is the only kind of open question that is remaining. And it's not a simple question by any means. It's fundamental to the field, basically. And so here you have options, do you collect more data? Do you do data augmentation? Do you uh, implement regularization? Use change the optimizer that you're using to train your network? And it turns out that the only thing that will not help in improving the overfitting problem is changing the optimizer, right? Optimizer does not have any role to play in uh, whether your model is overfitting or not, right? Optimizer only kind of deals with how well your model converges on the training data, right? So this is not going to do anything. Regularization obviously will help because it constrains the model in important ways, right? So you can have like L2 regularization, which limits the weights, the size of the weights, limits the values of the weights. You can have dropout, which is a type of regularization where you force, where you randomly switch off parts of the network, right? So you force the network to become smaller during training, right? So all of those techniques will work. The other way to deal with overfitting, of course, is you just increase the amount of data that you train the model on, right? So, and this can be done by collecting more data samples, or it can be done in a synthetic way by using data augmentation, right? So when you're thinking of regularization, you're thinking about the model size, the model complexity, or the model size, uh, and regularization directly kind of impacts how powerful the model is during training. When you're thinking about data, you have to think about the relative size of the data compared to the model, right? So when you're increasing the amount of data, then your model relatively becomes smaller compared to the data, right? And that is also going to help you to deal with overfitting, right? Because now you're going to see more and more samples, and you know uh, your model can no longer overfit on the training data because you have more of it, right? So yeah, and then another problem on similar lines, right? Where given we are given a situation where you have extremely high training accuracy, but you have very low validation accuracy, right? And the question is, how do you reduce the difference? So obviously, in this case, what you have, the problem that you have is a problem of overfitting because your training error has gone down extremely, but your validation error has is high, right? So the way to reduce this difference, obviously, you have to use one of the techniques that we talked about earlier, and only one that matches out of these options is dropout, which is a form of regularization. So you apply dropout, and hopefully that improves the situation, right? then, so this question is about parameter sharing, and the which of the question it asks which of the following types of or architectures of neural networks uses parameter sharing. And I'll just be brief with this. So The answer is convolutional networks. So basically, in convolutional networks, there is the concept of a filter that is applied across the image, right? And basically, the same filter is applied across the image, right? So if you consider two of the pixels in the output, what happens is that this pixel has been generated by applying the filter in this position, and this pixel has been generated by applying the filter in this position. But in both of these cases, the exact same filter has been applied, right? In fact, the exact same filter has been applied for all of the pixels in this convolution output, right? So what this means is that even though the number of neurons in the input and the number of neurons in this convolution output can be very high, the number of parameters that actually describe this transformation is very small, right? Because the number of parameters is is limited by the size of this filter, which is typically very small, right? So the typical filter sizes that you encounter in neural networks are in convolutional neural networks are like 3 by 3 filters or 5 by 5 filters. Uh, in fact, there's a lot of uh, there are a lot of networks you'll find that heavily use 1+1 filters, right? Is the extreme case, right? And they're all like functions on how to limit the size of the model, right? So if you use a smaller filter, obviously, the size of the model will reduce greatly, right? And there are all kinds of tricks that you apply with filters, with convolutional layers, right? And then one of the methods of dealing with overfitting. In this case, overfitting is described as a function of the number of epochs of training rather than the model complexity, right? So basically, you're training your model, and at some point, you hit that optimal solution. And then what happens is that after you hit that optimal solution, even though your training error continuously goes down, your validation error starts to increase, right? And in this case, early stopping technique, you basically keep a track of the minimum validation error that you are able to achieve, right? And once you have hit a particular minimum error, you apply this patience parameter, right? So if the patience parameter is 3, then once you have hit, so in this case, you have hit the minimum validation error at epoch 2, right? And then you wait for 3 epochs to try to see if this minimum validation error can be further improved. And in fact, it does not improve, right? So even after 3 epochs, it is still 1.9. So at the fifth epoch, you run out of patience, right? And then you stop the training process and you return the model as it was on epoch 2, which is when you had actually encountered the minimum validation loss for the first time, right? Right. So, and finally, this problem, which is the last one that we saw. Right. So yeah, so this is the last problem. Basically, every node that you apply dropout on can be either in the on state or the off state, which means that the number of configurations that are possible is 2 to the power of number of nodes, right? 2 to the power of 25, because there are 25 nodes that are there. So I'll do one thing now. I will uh, yeah, I will yeah, I wanted to show training example where we apply these techniques, right? So we have these techniques of regularization or dropout specifically, and uh, have mm, yeah. So we'll briefly go through like a simple example. This is something I have done in earlier sessions as well. So yeah, we set up our imports first, right? With TensorFlow, set up our data set, just MNIST, right? And we split the data into train and test, obviously, right? So we have train data set and test data set, right? Which is important for sanity check of your model training. uh, Test error, the validation error will basically tell you how good your model actually is, right? And then, so we apply normalized image, where we can convert the input to floating point values and normalize by 255, which is, so images are stored as 8-bit, unsigned 8-bit integers. So they range from 0 to 255. So you divide by 255 to make them go from 0 to 1, right? And then you apply patching with Rancelga 15. Finally, so we create a model. So here, this is very simple. One hidden layer model. So there is one dense with 1,000 neurons. The input shape is 28 by 28, which we will flatten to 784 uh, to 784 size, right? And then there is a dense 1,000 neuron dense layer activation segment distributor, right? So, right, and then so you can apply dropout, but let's see what happens with or without dropout, right? So we have 74 by 1,000, 784,000 plus 1,075,000 plus 7,840, right? Plus 10, right? 7,850. So it will be like 790 something thousand parameters, right? Which you can confirm with this model summary call. So see, yeah, like I said, 795,010 parameters, right? So you have flattened dense and another dense. Output is 10 uh, 10 neurons because they are 10 digits, right? Similarly, we will also define CNN model, right? So this is a convolutional neural network. Here we have the convolutional layers. So this layers.conv2d is a 2D convolution layers. And the way that this is defined is by saying we are applying a 3 by 3 convolution with 32 output, 32 output channels, right? Obviously, input channel, input size is 28 by 28 by 1 because it's a monochromatic image with one channel, right? And then after every convolution stage, we apply what is called as max pooling. So all of these kind of details will be seen later. So I'm not going into details with these things. They'll be covered in a later week. But we will see what is relevant to this week's discussion, right? Which is that, so here, this is a simple, there is a single hidden layer, right? And it's just, 2-layer network with a single hidden layer. Whereas this has so many layers, right? So there has this one conv layer, two conv layers, uh, three convolution layers, uh, plus another dense layer, and then finally output layer, right? Fully connected layers. So this is a 5-layer network. Uh, of course, max pooling does not have any parameters, but even though it is like a deeper neural network, what you see is that the number of total parameters is substantially smaller than the number of parameters we saw over here, right? So yeah, so you have very few parameters, and this is because the convolution parameters are shared throughout the image, right? Because they are shared parameters, the number of parameters that you actually get is pretty small. So now you generate the model, compile with Adam optimizer. So this is our fully connected model. Let's train the fully connected model, right? So we're training it for 10 epochs. Let's see what we get, right? So as you can see here, uh, our training loss and the training loss has gone down significantly, but our validation loss is kind of stuck, right? So training loss has gone down to 0.01, and the training accuracies are at like 99.7%, but your uh, validation accuracy is 98 point something, right? So this is so there is a significant difference between the training and validation losses. And in fact, you can see this here, right? So your training loss has gone down like this, but your validation loss or test loss, whatever, has kind of stayed stagnant as it initially reduced, but then it became stagnant, and the difference between these two are constantly increasing, right? So this is a typical, overfitting case, then a typical kind of situation that you would encounter. So let's see if we add dropout, we'll see if dropout helps, right? So we add dropout and we create the model again. We have to compile the model again, and then we train the model again, right? So remember that this was at 98 point something, 98.08 was the final accuracy after 10 epochs. So let's see what happens with dropout, right? Uh, yeah, so something that you can notice here is that the training accuracies are not going up quite as fast as they were that as they were in the earlier training run, right? You have uh, there is still like a difference between them, right? So this one has gone up to 99%, whereas this one is still at 98.24 is the validation accuracy. Uh, yeah, it's so this is slightly better, right? In the previous example, you were hitting the maximum validation accuracy that you got was around 98.24 to 4 or to 6. Here you are getting slightly better, you're getting 98.38 or something. So, and the difference is not quite as extreme as it was before, right? So you can play around with these values, right? So you can set a slightly higher dropout. You can even set this before, you can even set this at the input stage itself, right? So you can do something like this, and then this. So now we have a little bit more dropout, right? And yeah, so you get something, hopefully, most likely, most of the times you'll get improved performance. How much improved performance you'll get is variable, it depends on how you depends on a variety of factors, not all of which are in our control, right? But typically, when what you will see is that the uh, the validation performance will be more stable when you have dropout or when you have regularization compared to when you do not have it, right? So there will not be any wide swings where your validation accuracy gets significantly worse, right? So your validation loss will not have these wild up and down swings where you know what accuracy you actually achieve will be very dependent, would be very dependent on where you stop the training, right? Without dropout, but with dropout, it doesn't really matter, right? It kind of stays stable, right? The values kind of stays that stable, and that is typically what you would get. And in fact, it is good because then you don't have to uh, give extra thought about when should I stop the training. You can just stop it whenever it is sufficiently good, and you don't need to employ separate heuristics to figure out when to stop the training, right? So now finally we will do with the convolutional network. Remember that the convolutional network, even though it is a much deeper network, it has fewer parameters, and these fewer parameters are in fact much more capable, as we will find out, right? So the fully connected network was getting 98.3738 at best, even with dropout. And this one has already kind of blown it out of the water, right? So even with the fewer number of epochs, I'm just training it for 5 epochs, and this validation accuracy has already gone up to 99 point something, right? Which is a significant improvement. It is almost 50% improvement in the error rate, right? And all of this is because is happening because of this implicit parameter sharing that this model has, right? Even though you have a lot of neurons, you have fewer number of parameters, right? And that makes the model more powerful. Paradoxically, also, you can think it makes the model more powerful, right? So yeah, so this is the end. So this one can so this you can say demonstrate our parameter sharing with CNNs, right? So we have shown, how. So we have shown like an empirical example of how parameter sharing can help, and we have shown an empirical example of how regularization-based methods, for example, dropout can help, right? And yeah, I think that is probably that's the end of this. If anyone is having questions, you can ask now. Yeah, obviously you can add noise to your data, right? And that can make your model more robust, in fact, right? Because adding noise is very similar to data augmentation, right? Where data augmentation, you are applying these transformations adding noise is also kind of doing. So you're adding like a random noise signal to your data, right? Which is again similar to kind of generating a new sample, right? In a way. So yeah, you can add noise to your training data, for example, and that will make the training more robust. In most cases, it will make the training more robust in terms of overfitting, right? So you can add noise. Obviously, you can add more samples, and that will have an effect as well. You can do data augmentation. In this example, I'm not doing data augmentation, but yeah, you can do it. In fact, there are very standard methods to use data augmentation for image-based applications, right? So there are all these functions, well-defined functions, horizontal flip, vertical flip, uh, random crop, all these things that you can use, right? So yeah, you can always do it. In fact, maybe let me share this. So can so you can see this and uh, maybe it's like you can do take it up as an exercise to implement or include data augmentation in these in this training set, right? So you can implement data augmentation for the CNN model and see that whether it improves the performance even further, even though it's kind of already hitting the maximum, almost the maximum levels that it can, uh, with like 99 point something percent. But even then, you can even go higher. I think CNNs on MNIST, you can go as high as like 99.7, that much. So we can try to implement data augmentation in this model and see whether that works, right? Yeah. Ha ha ha. I will make sure to share, change the uh, mm, yeah, see this. So you can view it hopefully, and then you can save a copy in your own drive and you can play around with it. Right? Mm. Uh, Link to the folder containing slides is provided as through the course. Mm. ANN basic. ANN basic. Uh, okay, I think there are no more further questions, right? Uh, okay, since there are further questions, I'm going to end this call. Thank you for attending.